valence electrons are the electrons in the outermost principal energy level. For the main group, that's just the highest principal quantum number. So we can see that from the period on the periodic table, the row number. The group number, using the 1A, 2A, etc. numbering system, corresponds to the number of valence electrons. So if we look at oxygen, it's in group 6A. That means it has 6 valence electrons. So the valence electrons are in the highest principal energy level. Electrons in the lower level are called the core electrons because they're inside, like the apple core. And those valence electrons are the thing that affects the physical and chemical properties of an element in a big way. When we look at the periodic table, which was originally ordered by increasing mass, we see that the reason that elements in the same column have similar properties is that they have the same number of valence electrons. So this is an abbreviated part of the periodic table. We left out this gap in here. But here, hydrogen, lithium, and sodium all have 1 valence electron. Beryllium and magnesium have 2 valence electrons. Their group number is 2. Boron is in group 3A. It's got 1, 2 electrons here and a third electron there. So it's 2s2, 2p1, 3 electrons. Oxygen has 6 valence electrons. Neon has 10 valence electrons. Oxygen and sulfur have some similar properties. They both have 6 valence electrons. The number of valence electrons has a big effect on the behavior of an atom. So let's write an electron configuration for phosphorus and identify the valence electrons and the core electrons. So I'd like to do an orbital diagram first. So how many electrons does phosphorus have? 15. So 15 electrons. So let's make our boxes here. There's 1s and 2s and 2p and 3s and 3p. Up to this point, things are following the regular order. There's no interaction here. So 15 electrons, let's stick those in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then we could write the electron configuration from that. 1s2, 2s2, 2p6, 3s2. And how many are in the 3p? 3. So there's our electron configuration. Yes?
Are we not worried about the charge that it has? The phosphorus?
That's a good question. What about the charge? We're looking at neutral atoms. We're not looking at the ions. So there's no charge. So it says identify the valence electrons and the core electrons. So valence electrons, what we're doing is we're looking for the highest principal quantum number in the hotel, the highest floor that has anybody staying on it. So that would be 3. There's two sublevels there. They both have electrons. And so the valence electrons are all of these guys. Those are the valence electrons. They're in the highest principal level. They have the highest n equals 3. All of these other electrons are the core electrons. So these are core electrons. How many valence electrons are there? 5. 2 plus 3 is 5. What group is phosphorus in? Group 5A. And how many core electrons are there? 10. Any questions? Then I'm going to show you how you can find that ordering in the periodic table. We can divide the periodic table into 4 different blocks that represent filling of the 4 different kinds of quantum sublevels, S, P, D, and F. The group number for main group elements equals the number of valence electrons, and the row number for main group elements is equal to the highest principal quantum number. Okay, so here is a color-coded periodic table. Over here in blue, this represents the S block. Pink represents P, yellow represents D, and green represents F. Now, how many electrons fit in an S sublevel? 2. How many columns are in this section? 2. How many electrons fit in a P sublevel? 6. How many columns in this pink section? 6. How many electrons fit in a D sublevel? How many people can stay in the D room in the quantum hotel? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. How many in the F? 14. If you count those, there's 14. Isn't that kind of trippy? Mendeleev put the elements in this arrangement. He didn't even know what electrons were. We've got them all lined up like this. Quantum mechanics is discovered decades later, maybe a century later. Yeah, it was a century, well, anyway, long time later. And now we understand that the electrons and how they are arranged fits perfectly with this structure of the periodic table. So we just did phosphorus, right? So here's phosphorus, whoops, right here. And what we're showing on this periodic table is not the full electron configuration. What we're doing is we're showing the configuration past the previous noble gas. So for phosphorus, you could abbreviate that as neon in brackets, and then 3s2, 3p3. Oops, that's not an S. So here's neon, and then you come over here. This is period 3, so this is 3s, 1, 2, and this is 3p, 1, 2, 3. So you can actually count through and find all of these. So this is 1s, and helium's over here because helium and hydrogen are the little brothers. They're squirrely, and they sometimes hang out where they don't seem to belong. He's here for some reasons, but other reasons he kind of belongs over here. So 1s2, 2s2, this is 2p, it's period 2, 2p, 6, 3s2, 3p up to 6, and now here, this is the S block, 4, 4s2. What happened to the 3d? It's higher in energy than the 4s. The 3d is hiding here. So for the d orbitals in this transition metal section, the principal n is going to equal the period minus 1. So this is in period 4, right? Period 4. But this is the 3D sublevel. I like to think of it as being sunken, right? It looks like we're going down steps here, and it looks like this should be up here if we have a nice pattern. but it's sunk down a level. So if that helps you. So that's 4s2. The D level is sunken, so this is 3D up to 3D10. Now we're back into the main group. This is 4 again. 4p up to 6, 5s, and here comes another D. Is this 5D? It's 4D. 4D10, 5p6, 6s2, and then what's up here? 5772. That's not how numbers go. This group down here belongs right in here. And the one we have on the wall, mostly because of the space on the wall we have available, is cut and put together like it really should be, but it doesn't fit on a screen or a piece of paper very well then.
So would that be a period minus 2?
Yes. So for the F block, N is going to equal the period minus 2. So we're coming along. This is period 6. The yellow would be 5D, but the green is 4F. So this first one would have 3D1, and then for reasons that we're not going to go into, you start putting them in F. Now things get a little funky here, like why is this 4F1, 3D1, why isn't it 4F2 or 3D2? We're not going to worry about that. But this would be 4F, then we come back, finish out 5D, 6S, I'm sorry, 6P, 7S, and then 5F, and 6D, and 7P. And so the order, that weird filling order, is in the periodic table. So you can find the end of the electron configuration a lot like reading coordinates off of a graph. So for example, if we wanted to look at polonium, the end of polonium's electron configuration is 6 P 1, 2, 3, 4. That's the last term, 6p4. Any questions? So if we were doing chlorine, we could do the, we can represent the inner electron configuration, the core electrons, as a noble gas, and then just write what comes after the noble gas. So that would be 3s2, 3p5 for chlorine. So let's practice. Let's determine the electron configuration for bismuth. So bismuth. Bismuth is Bi. First thing is to find it on the periodic table. So what does it end with? What row is it in? 6. And this over here is the P block, right? 1, 2, 3. That's going to end in 6p3. So we could do the noble gas shorthand. What noble gas would I use? Xenon. Wherever this is, I'm just going to go up one row to the end, and that's the previous noble gas. So I could use xenon. Then after xenon's electron configuration, I've got this, which would be 6s2. And from 6s2, oh, I've gotten into this messy part here. So we're going to skip that guy. We're going to go to here. This is row 6, but this I have to drop down 2, 6 minus 2. So this is 4. 4f, we're going to go all the way across. How many electrons would that be? 14. I don't know why I didn't ever notice this before. The F has 14. 14 starts with F. 4F, so we're going across here. We got those guys. We got these guys. And then we have to go back and catch these guys in here. So this would be D. We'll go, oops, went too far. So the D block is period -1, so this is 5D, and we're filling all of them, so that's 5D10. And then in the P block, this is the main group again, so it's back to the same as the row number, 6, P, and we're counting over 1, 2, 3. Any questions?
How many valence electrons?
That's an excellent question. What do you think? 5. So valence electrons are in the highest principal quantum level. So we're looking at all of the large numbers here, and we're looking for the biggest one. So the largest one is 6. There's 6s2 and 6p3. They're both on the 6th floor of the hotel. We have to count all the electrons there. 2 plus 3 is 5. And that lines up with it being in group 5A. So how would we do the whole thing? What if they didn't want the shorthand version? Well, just start at the top. This is 1s, and I'm going through 2 blocks, 1s2. And what's this part? 2s2. And over here, 2p6. And this, 3s, 2, 1, 2, 3, 4, 5, 6, 3p6, 4s2, and this is D, but it's one less. It's not 4D, it's 3D, 10, and then this is back to normal, 4p6, 5s2, sunken again, yeah, 4d, 10, 5p6, 6s2, 4f14, 5d10, 6p3. You see how that works? A couple of things you have to remember. For these, the D block, you have to, the principal level is going to be the period -1, and for the F block, it's the period -2. But like if you forget how many electrons could be in the D orbitals, just count the D block. There's 10 columns there. It's 10 electrons. This is 14. This is 6. That one's 2. All the numbers are right there. Any questions? Okay, let's write electron configurations for chlorine. So let's do the noble gas versions. So what's the noble gas right before chlorine? Neon. And then looking at the periodic table, what's after neon? 3s2. And we come over to the P block, and how many? 5. 3p5. If you're not seeing that, please ask me a question. It's harder when you're doing it with your finger up in the air, pointing at something. It's a lot easier if you can actually draw on your periodic table. Here's an idea. You might stick your periodic table inside one of those plastic pockets, and then you can use a dry erase marker and draw on it and erase it and draw on it and erase it. Okay, what about silicon? Same noble gas. So after the neon comes 3s2 and 3p, but we're only going 2 blocks in, so there's only 2 electrons in there. What about strontium? Well, what's the noble gas previous to strontium? Strontium's in group period 5. Yeah, so we'll go up to 4. And for 4, we've got xenon. No. Yeah, it's krypton. At a weird angle, it's hard to track that across. Okay, krypton. And then what's next? 5s2. Done. Let's do the full thing for oxygen. Oxygen's pretty small. What's the first one? 1s2, 2s2, 2p4. One way to check at the end is add up all the electrons. 2 plus 2 plus 4 is 8. Is that the right number? Yeah, 8. For these in the noble gas, you look at krypton. How many electrons does krypton have? Well, it's got 36 plus 2, 38. Strontium is element 38, so I've got at least all my electrons accounted for. Any questions? We'll save this for later.